be able to mention to everybody who will talk. Okay?
Okay, but if there is not presented, will be other people from Brazil who can.
Of course.
Yeah, okay, excellent. Okay, nice.
Some of them could be the minister, could be nominated the minister.
Okay.
So I will try. The first one will be this one. Oh. He or her. Him or her.
Okay, perfecto. Perfecto. Bien, entonces creo que ya podemos empezar. Todo está listo. Albino, ya puedes empezar la moderación. Empezamos.
Good. Stuart, I will make the introduction in English and then I will change to Portuguese and Spanish, or better in Portuguese. Yeah. I think you can follow.
Thank you. No problem.
So, good morning, everybody. It's my pleasure to introduce you, Professor Doctor, as they are nominated in the University of São Paulo, my good friend Carlos dos Santos. Carlos is responsible, one of the men, women who were responsible of putting this Escuela de Ingeniería de Lorena in the scientific map in the world. They have been working there long time. They did not belong to the powerful University of São Paulo. And about 10 years ago, I guess, Carlos. Yeah.
Almost 15.
15 years ago, the University of São Paulo discovered that the Escola de Engenharia de Lorena was so powerful that they managed to catch them and put them in the USP agenda. So now, Escola de Engenharia de Lorena belongs to USP. So he has been working hard to build laboratories, and since some time ago, he is working also in theory as a theorist. By the way, a good theorist, and he has very nice ideas. And this is, as far as I know, unless he is hiding things from me, this talk is about the last article he submitted to publication. So I will not tell you how many papers he published, how many students he supervised. I can assure that
it's not too much.
It's a lot. But okay, let's go further. So, Carlos, again, you are very welcome. Welcome. Before you start, I should tell something about the LAFMAT network. This network is founded by several universities in Latin America, starting from Universidad Nacional Maior de São Marcos, no Peru, a decana de las Américas, Universidade de Barranca, Peru, Universidade Nacional de Colômbia, em Bogotá, Universidade del Norte, em Colômbia, also Universidade de Barranquilla, also em Colômbia, Universidade de Zulia, em Venezuela, Centro de Investigações de Materiais Avançados em México, Sinvestaf em México, Universidade Católica del Norte em Antofagasta, Chile, Universidade San Sebastián em Puerto Montt, Chile, University of Cambridge and University College London, Universidade de San Martín, Iteca, na Argentina, Universidade Federal Rural do Rio de Janeiro e Universidade Federal de Pernambuco. I guess I forgot no university. So it's our pleasure again. It's your pleasure to have you here. Please be free to start your talk. Thank you again.
Good morning, everybody. Oh, Albino, thanks for the introduction. You are very friendly with me. So it's nice to be here with you. I liked a lot this Red LAFMAT network, and I asked Albino to put my group inside sometime, so we have to work on that. Okay, let me try to talk about this manuscript or this presentation. This work is kind of work that started in my mind almost 30 years ago. I said 30 years ago, when I was doing my PhD, and I was working on electrical current on superconductors, and then some stuff bothers me a lot. And then I tried to think about it. Someday, 2 years ago, I had a nice idea, and then provide me this opportunity. So the basic idea is talking about electron scattering and the T-square dependence. So we are taking account the electrical energy in a Fermi gas theory. This is kind of the main idea. And then we use the effective Bohr atom and the Mott criteria for metal insulator transition to add something in this theory, this model. And this this provides us a kind of relation between effective Bohr atom and Fermi gas. And then appears I put this title, the electrical and magnetic force acting on electron at 0 Kelvin, okay? And then this provides us a model, an idea, and then electron moves like a helical, and I'll show this. And then the motion of the electron provides the orbital magnetic moment and the spin in very simple way, and I'll show you. And then a new picture for mean free path appears, and then we describe this electron scatterings, and then some other observations. Final remarks, and I'd like to do some acknowledgements. It's very common to see data like those. At low temperature, resistivity must scale like zero value, whole zero, and T-square dependence. And if you plot like a whole versus T-square, you should see a linear behavior. And this linear behavior provides this parameter that could scale as a function of Fermi temperature. This is very common in people that study electrical properties knows that this is electron scattering. Okay, and this is very important in several types of metals, like conventional metals, copper, transition metals, superconductors, isotropic and isotropic superconductors, and also heavy fermion superconductors and high temperature superconductors too. And also you see this the superconductivity here in this material, for example, and T-square is there. Okay, so this is another way to plot this T-square behavior. And then we would like to understand a little bit more about that. And if you go to the literature, you find this kind of plot. Those are very old plots. They scale this A parameter, prefactor A parameter in T squared, resistivity behavior as a function of gamma squared. Gamma is the Sommerfeld electron constant in heat capacity. And then you see the kind of empirical linear behavior with gamma squared. Also for heavy fermions, this appears too. And then Benya, Kahan Benya, is a very nice researcher. He worked with us years ago. He's a nice physicist. He came with a nice idea to plot all this stuff together. And then he notes that there are two kind of lines, this Rice behavior and the Kadawak-Woods behavior. And those two lines are here. And then after looking at this data, a lot of data, he came with this idea. The up parameter has to do with this equation. This is kind of quantum resistance. This is the Fermi temperature, and there is a kind of L quad has to do with this dissipation or mean free path. And then you see here the number for Rice scale and Kadawak scales. It's not 1.6 nanometers and 40 nanometers, and those scale in these lines here. And then our idea is try to understand those behaviors, okay? And then what we have done? Oh, just take the Fermi gas theory for electrons, free electrons. Everybody knows that this is the Fermi density, this Fermi function. And then you see this temperature dependence as a function of Fermi energy. And then at 0 Kelvin, you should have no electrons above the Fermi level. Okay. Also for the denser orbitals, this is the line when you include this function, then you see this density of charge as a function of energy at 0 temperature like that. That's everybody knows, it's very common. So at 0 temperature, strictly, no charges are available to carry the electrical current. So let me, then thermal energy is important parameter which controls the number of electrons to move above the Fermi level, leading to the electrical current. So the question is, exactly at 0 Kelvin, if there is no electron above the Fermi level, how they can carry the current, the electrical current? That's the one important and old question. So everybody could say, oh, some outmost electrons have already Fermi energy at 0 Kelvin. Yeah, that's true. They have Fermi energy. They move, but their energy is related to the orbital in atom. That's the way they have energy. So that comes from this. In our opinion, the energy at 0 has to do only with orbital kinetic energy. And that's related to the, we call equivalent Bohr atom that I'll show in some minutes. This equivalent Bohr atom, it's related to the Mott criteria for metal insulator transition. And this is related to the effective Bohr atom. Let me show you sometime, this time. For example, this is the copper, a simple idea for copper. And the idea to have the effective Bohr radius is like this. You put the core of the atom, the the central mass together with the electrons and leave just one electron alone. And this is kind of Bohr atom, right? Like hydrogen. So this is the kind of equivalent Bohr atom. And in this situation, you can calculate this radius. This is the effective Bohr radius. And this is calculated by this equation. Very simple. It's just taking like a hydrogen atom. And then you have the effective mass, and then the Bohr radius, effective Bohr radius. And then you can, in our idea, thinking about the Fermi velocity relates to the Bohr velocity in this model. And that's the base for our work. If you look at the Bohr criteria, the mod criteria, sorry for the dogs here. If you have the mod criteria for metal insulated transition, there is a clear relationship between density of charge and this Bohr radius. It's given by this equation here. And this is important because just you have the Bohr here, radius here, the atom, a Bohr atom, the effective Bohr atom. And then there is a distance between two atoms. And depending on the distance, you have the insulator, a metal, or you are in the threshold. Like if you have those guys far away, you have an insulator. If you are at a certain value, it's a 0.25. So there is a kind of connection, and then you start having electrical current through the sample. And then if you have many spheres, Bohr spheres, so you have a very nice metal. And then that's why you have this metal insulated transition. So let's take the following idea. Let's take the Bohr atom first, just the Bohr atom, the hydrogen with electron. So you have the electron, the Bohr velocity, the radius, the Bohr radius. This electron is running through the orbital, and then the orbital must take a time to give one turn. There is a current. This current is just a current, the electron charge divided by the time, or the rotation time, or one turn, for one turn. Then you have the magnetic moment, the orbital magnetic moment. So this distance here is lambda by 2 pi. Lambda is the de Broglie h over mv, and then the current is just E over tau, and you can calculate tau by dividing the lambda over Bohr velocity. And the energy for this orbital here is just related to the velocity, and then it's half mv squared. And then you can use these equations here and just multiply and divide by h and E here. Then this is equal this one here. And then you can do the following. Use this expression here, the de Broglie wavelength, and then you got this one here. And this is the magnetic flux quantum, phi0. And this is the current. And then you can use the following idea. The energy of the electron in the last in the orbital is equal phi0 I, where I is the electrical current here. So this, we call this electrical energy. And this is very interesting because remind us the Josephson current, or the Josephson energy. You see, it's just phi0 multiplied by the current. In case of Josephson junctions, this current is the critical current. So that's the one thing that makes me think about this idea. So let's take, for example, copper. And as I showed before, if you use copper, the density of charge in the copper is 8.49, 10 to 28 charge. So if you use a Bohr, effective Bohr atom, so this radius here is different, this velocity here is different, so we can change this time here, and we can change here, and then using the firm gas theory, this is basic equation in Kittel books, for example, you can calculate the energy, the firm energy, the potential firm energy, the potential firm level, the temperature, the firm velocity. So these values are those here. This you can find too in the books. And then if you use this idea here, you can calculate the Fermi current. So these ideas for many people is very strange. There are some authors have done this before. And so there is a kind of connection between the Bohr velocity, the effective Bohr velocity, with the Fermi velocity. So this is kind of a connection between those two velocities. This is not common. People generally don't make this kind of connection. But we are trying here is make a connection between the Fermi velocity in the firm gas theory with the Bohr, effective Bohr atom. You know, it's not a Bohr atom, it's an effective Bohr atom. Remember the copper, when you put electrons all together and have kind of a Bohr, equivalent Bohr atom, okay? Okay, let's do the following. Let's take let's remind some stuff about firm gas theory. First of all, the energy can be increased by the temperature after from zero temperature. And also you can do that based on the current. If you add some current, you add some energy, then you can add up both too. And then you can change the firm distribution by adding this phi 0I here. So when you have zero temperature, then you have this function here. And this function is kind of strange because people generally don't use this current right here, it's just temperature. But if you use the rest of the theory, then you find the following. This is the density of charge, that's the number of charges. So this density of states here, the blue line is this kind of conventional in firm gas theory. And this line here, black line, is for zero current when you don't apply any current. So you have this kind of behavior here. No charge are above the firm level. You are not applying any current at zero temperature. So there is no charge above this firm level. The charge is just running in orbitals through the atom. And when you add some current, for example, 5% of the Fermi energy, then you have this kind of behavior. This is very similar to the temperatures, right? Because the function is the same as the function for the temperature. So now you have a current and a charge above the Fermi level, so the charge can carry the current. Okay, let's think a little bit more about that. Here's the Bohr atom again. So here's the quantization of the one of the Bohr quantizations. The relation between the lambda and the Bohr radius is given by this one, and lambda is given by the de Broglie wavelength. If you apply the electrical field right here, perpendicular to this behavior, so probably you can see this helical motion of the electron. Okay, so here's the Bohr velocity. Here's the force related to the force, and then the electron moves this direction. So let's think a little bit about that. If you go to the Fermi gas theory again, you see that there is a quantization, and there is this quantization relates the lambda with 2L. 2L has to do with the number of charges per volume. So it's related to the density of charge in the metal. And then if you look there in the Fermi gas, you find this equation here. And this equation we can relate to this Fermi Bohr velocity. Let me do the following. If you use this equation, that's the same here, and compare those, you find this equation. So there is a kind of relationship equivalent between the Bohr velocity, effective Bohr velocity, and the Fermi velocity. Okay, notes that there is a kind of pi over 3 here term that is a little bit different because of this factor here, but it's kind of 0.314 over 3. Okay, it's kind of 0.3 per 0.14 over 3 difference. So there is a kind of relationship, and this is very strange. But let's go further. Let's take copper, for example. This is the copper LEDs. So if you look here, you see these two balls, two coppers, and as the distance between two coppers is kind of 2 RB, the Bohr radius, effective Bohr radius. So the force between two charges in this distance is given by this one here, by this equation. And if you use L from the other equation, from the Fermi gas theory, then it's easy to show that RB is related to this L, and it can put here, and you find this equation. Now, there is a kind of electric force related to this L. And then, if you go back to this, the Fermi energy, then you can find that's possible to show that VF over IF is kind of a quantum resistance. So the idea is when you have this kind of the electrical motion in these two atoms, then the resistance should be given by the quantum resistance. If you go in deep detail, then you can show that the quantum resistance is related, in fact, to this idea here. But let me go further because of the time. So if you accept that the quantum resistance is related to this problem, so the power energy in this dissipation is given by R multiplied by current squared, right? This is the power, the Schur self-heating. So then the power is just the force multiplied by V. This is very simple. And then if you use that, you find that the power is proportional to E squared. And this C is the proportional constant here. Then if you go to the mathematics, you find this C as a function over pi Bohr velocity for the hydrogen atom and effective Bohr velocity for the copper, for example. So the force is given by this equation. And it's interesting because now you can see the electrical force is kind of proportional to the square of the current. And this reminds the magnetic force, right? Oh, I'll show you in a minute. For example, well, if you take the previous questions, you can just write down here. So alpha is an important parameter, and Sommerfeld constant. hyperfine Sommerfeld constant, and this is the electrical magnetical relationship. And if you put those in this equation, you find this one. And this one here remind us something. Just have another idea. This is the mean free pass. Mean free pass is just a firm velocity multiplied by the time of scattering. And let me think about the possible idea. This is very hard. This relationship, you can define a kind of mean free pass for the c velocity, for the speed of light. Okay, just let's take this way. So if you divide those equations, you can find this. But if you use this relation right here, you can find this equation here. Okay, this is very simple. Just put this in this place here. In the Bohr velocity, effective Bohr velocity over light speed of light, then you can use this relation here. And this reminds something. Just take two currents, parallel currents, and then two parallel currents provide a magnetic force given by this equation. This is the very simple book for undergraduate students. And if you look at this equation here and this one, you see kind of magnetic force. So you can think about to have two charges carrying the current, the same current, and then they provide a kind of magnetic force. If you define beta as a firm velocity over c, then you can find an equation that relates this force, this magnetic force, with the electrical force given by this equation here, where beta is this ratio, firm velocity over c, or Bohr, effective Bohr velocity over c. Okay? If you use the Bohr atom, the hydrogen atom, I mean, then the Bohr velocity effective is the Bohr velocity, beta is equal alpha, and then the magnetic force is alpha over pi multiplied by electrical force. And this is 3 orders of magnitude smaller than the electrical force. The magnetic force is 3 orders of magnitude smaller. That's very interesting. So let's go further and try to understand this mean free pass at the speed of light. First of all, if you have an electron running through the orbital, there is no Poynting vector. I mean, there is no dissipation, and then the product between E and B must be perpendicular. So if you use the lots of equations, previous equations, then you have a question: what's the possible value between the lambda of this movement here over the mean free pass? What is that? So let's think about it. That's one idea. This is a very hard idea. We just think about the following. This is alpha. Alpha is the 1 over 137. I don't know if you know this number, but it's a very important number. This is the one constant in the Sommerfeld theory. So the idea is that let me go further here. This is the atom. And then what's the C? Where's the C? Electrons right here is running through the orbital, right? With the Bohr velocity. But we have an idea. We had an idea, very, very tough idea. Instead, electron running through the orbital in this way. It runs like a, I would say, spiral, like a solenoid, okay, with a speed of light. Then, if you make some calculations, you find the number of turns, like 19,000 turns, to have the same equivalent Bohr velocity. So this is very strange, but curiously, we have this idea, and then I start thinking about, look at the literature, and then we find this nice paper by Oliver Consa, a Spanish guy. He published this paper in 2018. He said that the possible electron runs like a toroidal motion instead orbital one. And this agrees very well with us, with our idea. Let me go a little bit further. It's kind of a lot of stuff, right? So then in the final, we put all together. Let me go further. So to prove this, we have the following idea. Let's take the Bohr atom. Let's take the Bohr atom, the hydrogen atom. And then suppose that we have a center mass. This idea is very, very known. Just we have an electron, you have a proton, but then they move each other. So we have this kind of center of mass that's dislocated from the proton some distance here. If you use this idea, you have the proton running, you have the electron running, then you have a current by electron, you have the current by proton. The proton has the velocity, the electron has the velocity. If you do the calculations, you find this lot of equations here. And then, if you use the magnetic force for this situation, see here, you have a current here, you have another current here. They are running together, okay? So the magnetic force between those two charges is given by this equation. You see here, the magnetic force. This is the current by electron, this is the proton current, this is the distance between them, this is similar to this equation here, and this distance here is the mean free path, or the distance covered by the electron. So when you make some calculations, then you find that this LB must be equals Compton length over alpha squared. And then you recover the previous equation from here. Let me show you from here. I'm sorry, just a moment, please. Here, you recover this equation here. So we believe that this motion is makes sense. So it's kind of electrons running like a toroidal instead just orbital. And then look at that. How many minutes? 30 minutes. Oh, that's nice. Okay, so look at that. Electrons running like here, and then it moves like this way. The orbital velocity, this is the Bohr velocity, and this toroidal velocity is kind of the light velocity or speed of light. So if you see this the Bohr velocity, then you kind of have the conventional magnetic moment. But if you look at this running here, for example, this is the electron running in this motion here, is toroidal motion or helical motion. And you can see another electron if you have another one connected to this orbital for two spins in opposite side. So you have running in another direction. So you can see a current here and a magnet produced by this current here. And you have another current here and the magnetic field produced this way. So those two cancel each other if you have two charges running in the same orbital. So that's why you have this connection between the spins. And then let me show you something very simple and interesting. This is this radius here. We call it Compton radius. That's the Compton length over 2 pi. And then this area here, this blue area, is given by the sub pi r squared. So if you multiply the b, for example, this b over s, b over multiplied by s, then you find the phi zero. Phi zero is the quantum flux. And then if you multiply the current with multiplied by s, then you find the magnetic moment. And this magnetic moment is equal the spin, simply. So the simple idea is, if you have the electron running this way, the orbital moment is the conventional orbital moment. It's known. And spin is very simple. It's just related to this toroidal motion or a helical motion. Okay, let's go back a little bit. So this LC, this mean free path at speed of light has to do with the mean free path. Let's see. Here's, for example, a copper atom, and you apply the electric field, and then the electrons start moving in this way, right? Because it was running in orbital, and then you apply the field perpendicular to it, then it moves like a helical motion. And then this helical motion has a length. This length is called mean free path, okay? And this Bohr velocity is equal Fermi velocity. And in fact, if electron is running like a helical or toroidal idea in the previous slide, so electron is running like this image here. So the distance running by electron is much larger than L. Okay, let me go further. Just the final idea. Just let me show the final idea. This is the electron-electron scattering we use in this model. So this is the conventional resistivity, m over pi tau over e squared n. N is the density of charge. If you use this model, then you find this relationship with L. L is the cube from Fermi gas theory. L is the mean free path, and the other parameters is known here. If you use the angular moment from the Bohr equation, then you have this one, and you can substitute some stuff here to get this one here. It's just simple. Just multiply by 2 pi, then you find this way here. And here you can substitute lambda over 2 pi. And if you use those equations, then you find this one. I'm not going too much further here, just to show. And then LB is coming from the other figure. You can put together here, then you find this one. It's interesting. LC is a constant number. It's 6.2 10 minus 6 meters. So it's a constant, and it's a huge name compared to the mean free path, typically 10 to 14, 10 to 10, minus 10, sorry. And the time scattering is kind of 2.1 10 to minus 14 seconds. This is comparable to many metals. And then if you use this previous equation here, then you find this constant. Whole multiplied by n is a constant. Oops, I'm sorry. And then you see time is constant, the density is constant, in some regard, and at zero, if everything here is at 0 Kelvin, right? So let me go further in the thermal energy per charge in the scattering. If you notice in the beginning of the presentation, I showed you the power, electric power, right, relate to the electric force. And then if you take into account just one electron, you have to have this cube in the Fermi gas model. So you must correct the force, the electric force by this term here. And the energy for electron from here, running from here to here, is just the force, electron force multiplied by L. And this is if you use Fe from other slides, you can find this equation here. But to correct it, you must multiply by L over the mean free path, and then you got this equation. Okay, this is very simple. It's just a lot of work, mathematical work. But if you compare this number here, this is the energy for electron to go from here to here. This is the energy from here to here. You add as the energy by the current, okay? When the electron interacts with another electron, it transfers the energy to the other as the thermal energy for increase the temperature relate to the Joule effect. So this makes the system to increase the temperature. And then there is a heat capacity, the electron heat capacity. And then this energy increases the temperature of the system. And then you can show that this increase of energy is given by T squared. So if you use this equation right here, if you use here, you can find how the electrical resistivity depends on the temperature. And then you find this T squared. And then let's compare with the Benya and other guys' data. So if you calculate this Q here, you find this number. If you calculate A over T Fermi temperature squared, then you find this constant here, this Q. Or if you use the heat capacity, Sommerfeld constant, then you got this number here. So let me compare with the Benya's data. Here's the figure I showed in the beginning of the presentation. So this is the Rice line, and this is the Kadawak line. And this is the Benya's empirical finding. So our Q is given by this number, our A is given by this relation, and if you look in the previous slide, A is given by this equation here that's equal to Benya's equation, where L quad is given by this equation here, where lambda b is the Bohr length, just the Bohr length, and then we find the number 1.59 10 to minus 9 meters. If you compare this number with the rise line, you find almost the same number. So you can compare this model with this data here. So here's the A over against Sommerfeld constant squared. Here's our numbers. Here's the constant, and this number here is this black line here, and agrees very well with the Rice finding. Also, if you pick up all the data in literature and put together, you see this, the red line is the Rice line, and the black line is our prediction. So this relates to the Fermi temperature squared in the over, it's a number over Fermi temperature squared. So it seems to us that something is important here, because there is no previous theory to describe this line here. Okay, so we find this could be important. And finally, just to show to you, if you calculate very quickly here, if you calculate the central force right here, you find this number, or this force here is mc squared over r, and then you find this field here. It's a very, very, very high field, and Oliver constant find the same number. And then if you relate this central force with the electrical force, the conventional electrical force between the proton and electron, then you find this equation here. Interesting is, if you use instead alpha is V Bohr over C, instead using the Bohr velocity, use the effective Bohr velocity. So you can put beta here, and you use the central force here, then you find, unbelievably, you find the quantization of the one of the quantizations of Bohr. The other thing is, if you consider that when electrons is right here, there is a bigger force than here, so the motion is not like a very nice ball here, but it's kind of elliptical. And if you consider the elliptical, then you got the correction by Swinger for its spin. And then it's kind of alpha over 2 pi plus 1. This is the correction by Swinger finding quantum electronics in 49. The other thing, if you look carefully for the Fermi gas theory, you can find the Drude model. Just to give an idea, if you have a 1 meter long 12 gauge copper wire, which cross sections is 3.31 10 minus 6 meters squared, and the density charge is 8.49 10 to 828, carrying a current like a 1 ampere, it has 2.8 10 to 33 electrons available, which is, if you use the Drude model, then you find the dislocation velocity. It's 2.2 10 minus 5 meters over per second. So in this case, you have just 8.37 10 to 12 electrons carrying the current with the Fermi velocity. So there is a connection between the Drude velocity and the Fermi velocity. In the Drude model, all the electrons carry the current. In the Fermi gas model, just a very small fraction of the electrons carry the current. That makes sense. So there is the model also provides the equivalence between the Drude model and the Fermi gas theory. Also, you can find the electrical resistance, a quantum resistance on the law. It's just a question of put the questions together. I'm not showing this in detail. And you can recover the metal insulator transition equation by Mott in the metal insulator transition. The empirical equation is this one here. You can find this paper. It's paper by Edwards. And then you can find this equation here. It's very close. And finally, let me give my acknowledgements. So you can find this paper or my work these days in ResearchGate, in this link here. This paper, the manuscript related to this presentation, I put in the chat here for you. You can find it there. My email is right here. It's very simple, and I'd like to consider my colleagues in this work. All of them were PhD students many years ago. Mário da Luz, Felipe Souza, and Leandro Alves. I'd like to acknowledge you for taking time to see this presentation. I know that's tough, a lot of calculations, a lot of details. Some of them people don't know exactly, so it's hard, but it's kind of start. And then I'd like to say thank you, Albino, for inviting me for this hard work here. And then, obrigado, Feliz Natal e próspero Ano Novo para todos vocês. Albino, thank you very much, my friend. I'm here for possible discussion and provide some answers. So it was nice to be here. Thank you very much. You see, it's hard work, right? This work took me, just to let you know, man. This work took me like 8 months working 80 hours a day. That was a hard work because I had to learn about the Dirac equation, about the Swinginger spin moment, Mott criteria. So that was a little bit hard, but I guess something is right here, and I appreciate to share with you. Okay, so I hope people understand a little bit and can ask some questions and read the paper. Thank you very much, my friend.
Okay, Carlos. Thank you, my friend, for this very, very nice talk, very impressive results. I think I will need more than 3 years to understand all this stuff. Okay? But the first question I have, did you meet Rice? Did you discuss with Rice about these ideas? You cite Rice. Please go to slides behind. Do you understand me?
Yeah.
Oh, okay. Rice, did you meet him? Did you talk to him?
No, I don't. No,
okay.
I didn't. No.
I will not ask any question now because I know that people are anxious to ask. So let me mention again that this network put together several universities in Latin America, starting from the Universidad Nacional Maior de São Marcos, Universidade de Barranca, em Peru, Universidade Nacional de Colômbia, em Bogotá, em Barranquilla, e Universidade do Norte, em Colômbia, Universidade del Zulia, em Venezuela, o Centro de Investigações em Materiais Avançados no México, o CINVESTAF no México, Universidade Católica do Norte do Chile, Universidade de San Sebastián, em Puerto Montt, Chile, Universidade San Martín e Teca, na Argentina, Universidade Federal Rural de Rio de Janeiro e Universidade Federal de Pernambuco, em Brasil, e University of Cambridge, in University College of London. So, the presentation is now open to questions, and I would like to call first Professor Angel Bustamante. Professor Angel, are you there?
Obrigado, Albino.
Okay.
Muito obrigado, profesor Carlos dos Santos, por la palestra. Tenía una observación o debe haber algún comentario. En la última lámina, donde você coloca ahí el níquel, observo níquel con un comportamiento distinto de otros. Aquí, que está atrás de la otra lámina. Você ve que tem níquel embaixo ya. Ahí, ¿cuál es el problema con el níquel ahí?
Ok. Eu acho que aqui essa medida é a medida feita pelo Rice, né? Em 1969, mas ele mediu 2 amostras. E é muito difícil, professor, muito difícil medir a resistividade de metais em baixas temperaturas. Então, aquela extrapolação que você faz do regime de resistividade ao quadrado para calcular o valor do A, que é o que aparece aqui no eixo, o valor do A é muito difícil de ser determinado. Então, ele deve ter medido várias amostras e mostrou aqui os dados de 2 delas, tá vendo? Então, ele tem um erro muito grande. Observe que ele também observa erro na própria platina, tá vendo?
Também.
Então, esse é um problema sério de medir a resistividade nesses materiais. E se você lembra lá no começo, nas primeiras transparências, a resistividade ela decai muito, né, em função para baixíssimas temperaturas. Então, determinar o valor de A...
Perde a linealidade.
Isso, exatamente.
Sim. Agora, em esse modelo um pouco quântico clássico, se você pone, por ejemplo, ya tem un desvío con paladio, podría considerar, por ejemplo, tierras raras, que son ahora importantes, o modelo sería más relativístico, podría se pensarse así, no sé.
Muito boa pergunta, viu, Angel? Muito boa, porque assim, o que acontece? Se a gente sair do metal convencional, do metal que é isotrópico, a tendência é ele se desviar desse comportamento. Então, por exemplo, se você olhar os heavy fermium, eles não batem aqui, porque tem uma contribuição spin-órbita com certeza, e o modelo, como ele está considerado aqui, ele não leva em conta a interação spin-órbita, por exemplo. Tá? Então, na realidade, eu estou exatamente trabalhando, Angel, no sentido de olhar para a interação spin-órbita agora, para ver se a gente consegue encontrar um valor de comprimento, de comprimento que tem a ver com o livre caminho médio, que bata com a linha de Kadawaki-Woods, que é exatamente para materiais que são mais magnéticos ou são pesados, heavy fermium, tá? Muito interessante a sua pergunta. Obrigado por ela.
Obrigado, doctor Carlos dos Santos, y esperamos como Netflix a segunda versión. Muito obrigado.
Obrigado, Angel. Um abraço. Bueno, professor Davi, não lo veo. De Colômbia, não está. Não veio também o professor, então vamos chamar o professor José Fermín, de Venezuela. Fermín? Ah, está. Bem-vindo, homem.
Good morning. Muito obrigado, professor Carlos, pela sua palestra. Pelo menos para mim foi muito legal. Eu tenho uma pergunta para você, mas antes disso, eu queria lembrar que hoje, 17 de dezembro de 1830, morre em Santa Marta, Colômbia, Simão Bolívar. Então, foi uma data muito importante para alguns países aqui na América Latina. Bom, ok, professor Carlos, I would like to regard your helical model for the electron. Can you please put that slide?
José Fermi, pode falar em espanhol mesmo? Parabéns aí pela data de vocês. Eu não entendi sua pergunta, meu amigo.
Eu gostaria você colocar aí aquela transparência onde fala do modelo solenoidal do elétron. Pronto. Minha questão é muito naiva, muito simples. Seria ou é possível, então, falar que o elétron, nessa órbita, induz alguns efeitos indutivos dentro do átomo?
Muito boa pergunta, José. Deixe-me dizer, o efeito magnético num átomo mais, vamos dizer, tipo cobre, ele não deveria ser visto. Sabe por quê? Imagine se você tivesse uma bobina toroidal, certo? O campo fora da bobina toroidal, ele é zero.
Zero.
Por uma questão de simetria, certo ou não? Agora, tem um outro fator que é importante também. Isso para átomos pequenos é razoavelmente interessante. E átomos leves, vamos dizer assim. Olhe bem, a distância do raio de Bohr é centenas de vezes maior do que o raio de Compton. Portanto, esse desenho aqui está numa proporção equivocada. Esse raio aqui é 1, esse aqui é 100. Ou seja, esse toroide ele é extremamente pequenininho. Ele é extremamente estreito. Consegue entender isso?
É quase um fio.
Então, oi?
É quase um fio.
É quase um fio, exatamente. Então, isso, se você olhar sobre esse ponto de vista, você vai enxergar como se fosse a figura de baixo, que é a figura convencional do átomo de Bohr. Entende? Então, esse toroide, o elétron gira num toroide que tem um raio pequenininho, que é do raio do tamanho do Compton, tá? Que então seria algo como a razão entre o raio de Compton e o raio de Bohr é 1 sobre 137, que é exatamente aquele valor do alfa. Não sei se está fácil aqui. É o valor do alfa. Ele não está fácil aqui, tá? Mas entende isso?
Sim, sim.
Essa que é a ideia, viu? Agora, vai aparecer uma pergunta, se me permite, tem um minutinho, posso explorar. As pessoas vão dizer assim, mas você está dizendo que o elétron está girando com a velocidade da luz? Este modelo quer dizer exatamente isso. Só que o quanto que ele anda para frente? Ele anda para frente com a velocidade de Bohr. É que ele gira tanto que ele quase não anda para frente. Lembra a conta que eu fiz? O número é 19.000 voltas. Ele dá 19.000 voltas. Entende? Então, no modelo, o elétron, ele viaja com a velocidade da luz e não tem massa de repouso. Eu não entrei nesse detalhe aqui, tá? Porque alguns referis, por exemplo, já está 6 meses na mão dos referis, né? Um dos referis, por exemplo, está questionando o fato de, mas como é que fica a relatividade? Não, a massa de repouso do elétron, que é igual quase a massa do elétron no átomo de Bohr, tá certo? Porque o átomo de Bohr não é relativístico, a velocidade não é relativística, né? A massa do elétron é a massa do repouso, mas nesse modelo o elétron estaria viajando a velocidade da luz, e para isso ele não poderia ter massa na velocidade da luz, ele seria só uma onda eletromagnética com carga. Agora, aí tem uma outra história que, obviamente, eu ainda nem tive oportunidade de olhar, que seria a relação da história da carga, tá certo? Isso vai acabar levando a teorias ainda mais complexas que envolvem a questão massa-carga, luz, né? Tá? Legal, José, obrigado pela pergunta. Eu que agradeço, meu amigo.
Obrigado, José. Carlos, eu tenho um comentário. O seu elétron toroidal, vou chamar ele assim, posso chamar? Ele está acelerado, não é?
Acelerado em que sentido, meu amigo? Ele
tem uma aceleração.
Ele tem, porque ele tem uma força centrípeta. Ele tem uma força centrípeta, exatamente.
E ele não emite radiação, né?
Não emite, ele tem que ser conservativo. Mas eu vou te fazer a pergunta. Não, vamos, deixa eu te fazer.
Então, ele satisfaz ao postulado de Bohr.
Satisfaz.
Não, é só para entender que você não violou o postulado de Bohr.
Não postulei. Na realidade...
Pode falar.
Deixa eu mostrar uma coisa para você.
Por isso que Bohr não entrou em contato comigo. Você deixou ele quieto.
Meu amigo Albino, deixe-me dizer uma coisa para você. Bom, se você olhar para o átomo de Bohr, o elétron também está sujeito a uma força centrípeta, certo?
Certo.
E, obviamente, que não viola, não perde energia, porque atende exatamente a conservação da quantidade de movimento. Certo ou não?
Certo, é o postulado dele.
Exatamente, meu amigo. O postulado dele está escrito aqui na última equação da tela, tá certo? Veja bem, olha que interessante, Albino. Eu vou repetir um pouco isso aqui, já que a gente tem alguns minutos, eu suponho. Veja, a força centrípeta que você falou, essa daqui, ela é dada por essa relação, massa C² dividido pelo raio, não é isso?
Sim,
se você substituir o raio de cômputo aqui, você vai encontrar essa equação, tá certo? Agora, essa equação, se você buscar lá para trás, você vai ver que ela se relaciona com a força elétrica, tá? É fácil de ver, né?
E está constante e perfina aí no meio.
Isso, está constante e perfino, que você percebe que é 1 sobre alfa ao cubo, tá certo? Então, o que é interessante é o seguinte, se você tiver um átomo qualquer que não seja o átomo de Bohr, o átomo de hidrogênio, o que vai acontecer? O teu alfa aqui tem que ser trocado por beta. E ao trocar por beta, meu amigo, e usar essa equação, você vai descobrir que você chega exatamente na quantização de Bohr.
Tá bom. Aí vem o meu comentário, deixa as outras pessoas falaram, mas talvez aqui tenha uma dica para a pergunta do Ángel. Depois a gente discute isso, não está errado. Tá bom? Vamos convidar mais gente. Então,
Maravilha.
Depois de chamar o José Fermin, eu gostaria de chamar o Felipe Mondaca. Felipe? Felipe?
Sí, hola.
Olá,
Hola.
Felipe. Abre tua câmera, por favor.
Sí, gracias. Gracias por la presentación. Yo, nada más una pregunta así general. Noté ahí que hay muchos cálculos que los realizó con física clásica. Mi pregunta ahí, si también se puede hacer un enfoque de lo mismo, pero aplicando más física moderna, física cuántica. Eso, nada más, una pregunta. Gracias.
Obrigado, Felipe. Na realidade, a gente não considerou a aplicar, por exemplo, a equação de Schrödinger, por exemplo, tá? Porque é o seguinte, aqui precisaria olhar para um modelo relativístico quântico. E ele não estabelece essa questão do elétron espiralando dessa forma. Então, nós não conseguimos avançar para esse caminho ainda. Então, na verdade, a gente está meio se a gente copiasse o modelo de Bohr, Schrödinger, né? A gente está meio que alterando o modelo de Bohr para poder fazer essa sequência agora no modelo de Dirac. Tá? Porque a gente tem que resolver a equação de Schrödinger e Dirac agora, porque é relativístico. É quântico relativístico, tá? E aí a gente não teve a oportunidade de fazer isso ainda. Mas obrigado pela sua pergunta e sugestão.
Gracias. Hasta luego.
Obrigado, Felipe. Muy bien. Vamos a llamar o professor Sérgio Conejero. Sérgio, olha aí. Bienvenido,
Hi,
Sérgio.
good morning. Thank you very much, Professor Carlos, for your excellent talk. I have learned new things about it, so I'm very grateful for that. So I have a general question related to the Bohr model. You know, it's like an obsolete model that makes quantum and classic formalism. So I would like to know if you try, for instance, because for instance, for Schrödinger equation, you can solve analytically for hydrogen atoms, so you can try to obtain the same solution for both models. Have you tried that?
Sérgio, obrigado. Thanks for the question. I did it, but you have you gave me an idea. That's nice idea, because we can use the Schrödinger equation to solve the Bohr atom. I mean the hydrogen atom. So that's a good idea. So maybe we can find the mean free path for the atom, for the Bohr atom. So that's a good idea. Thanks for that. I didn't try it yet, but yeah, it's a good idea. Thanks for the suggestion.
So I have another question. In this model, so for me, it's quite transparent. Try to see or to study the orbit spin coupling. So I don't know if you already answered that. Or
I'm not able to answer this question yet, because we did put the magnetic moment, the magnetic energy in the model. So probably we have to change again the firm gas theory, taking into account the magnetic moment. So we didn't yet.
Not yet. Okay. Thank you. Thank you very much for your excellent work again. So.
Oh, thank you very much.
Thank you very much, Sérgio. Now I'd like to call Stuart Holmes. Stuart, are you there?
I'm here. Thank you. Thank you, Professor Dos Santos. Very interesting. I had to think very hard about my knowledge of this field. I have a couple of questions. So when you have the Bohr model, simple Bohr model, which works very, very well, I have to say, it has the dielectric constant of the material. And in some materials, like I think you showed indium antimonide, has a huge Bohr radius. And so the dielectric constant is very accurate for the material. But in some materials, Bohr radius is very small and the dielectric constant breaks down. But it appears that what you're doing here doesn't see that. There's no breakdown of the dielectric. Could you comment on that?
Yep, that's a very nice question, Stuart. Let's just took the slide here. Yeah, you mean about this guy here, right?
Yeah,
that's
exactly.
nice. But yeah, but remember, we are talking only about metals. Remember? So if you try to measure this property in metals, it's kind of not important. You know, for example, people have done Benya, for example, the author of this paper here. Oh, I'm sorry. Oh, I'm sorry. Just a moment, please. Benya, the author of this paper here, he talks about that. But you know, people find the dielectric constant in the insulator phase. For example, in strontium titanate. But if you remove the oxygen and make the sample like a metal, then you're not able to measure the dielectric constant. And in the model, supposedly, that's very strange, I have to say, I have to admit. But in the model, like the metal, you have this model has a kind of electron is in the Bohr model, an effective Bohr model. It's a kind of in vacuum, right? There is nothing between the proton and the core, the atom, and the electron. And interesting, in the paper you can find, we calculate the resistance and the inductance. Take a look at the manuscript. You see there, the model agrees with the literature regarding this vacuum dielectric constant. That's a very nice question. Thanks for that.
I had some other minor questions on the mathematics, but I'll look up some of the papers. that will help.
Thanks.
So thank you.
Okay.
Thank you again. Very nice talk. Thank you.
And thanks.
Thank you, Stuart. Now I would like to call Diego Lamas, Professor Diego Lamas, por favor. Diego.
Hola, buen día.
Buenos días, Diego. Bienvenido.
Obrigado, José. Obrigado, Carlos, por la palestra. Muy interesante. Yo quería consultar a você esa comparación que você hace con dados experimentales. Ahí vi que hay óxidos también de comportamiento metálico que você compara, que se apartan un poco de comportamento general. No sé se você tiene algum comentário de por que acontece isso.
Dá um minuto, eu vou levar lá na figura.
Sim.
Eu acho que é importante mostrar a figura. Pode ser essa aqui.
Sim.
Essa aqui.
Isso.
Então, na realidade, o modelo funciona muito bem para os materiais metálicos cuja densidade de portadores não depende da temperatura.
Uhum.
Então, se você medir a densidade de portador, por exemplo, no cobre, por exemplo, ou no titanato de estrôncio com tirada de oxigênio, que ele vira metálico, se você medir a densidade de portador, ela está constante com a temperatura. Nesses metais, o modelo funciona muito bem. Isso, na realidade, está meio que, na minha opinião, vinculado com a pergunta que o Stuart fez, que tem a ver exatamente com o fato de você ter um modelo que o material funcionaria numa espécie de modelo ideal, que é onde tem o elétron e o core do átomo e nada mais entre os dois, ou seja, seria vácuo entre os dois. Nesse caso, todos os metais funcionam muito bem. Então, aí você vai ver os titanatos de estrôncio com diversas dopagens, alguns metais como esses daqui de térbio, o cobre, até interessante que eles estejam aqui, e os metais mais de transição e os convencionais.
Ujú.
Não sei se isso responde a pergunta que você fez, Diego.
Sí. Y tiene algunos otros, ¿no? que apartan un poco, ¿no? Tiene ahí algunos otros.
Que não concordam.
Mm.
Esses azuis, vermelhos, eles não concordam, de fato, mas eles têm duas grandes características nesses materiais. Eles são não anisotrópicos, ou seja, eles são anisotrópicos, portanto, as propriedades elétricas são distintas nas várias direções e, como consequência, a densidade de portador não é constante com a temperatura. E outros materiais que são os heavy ferro. Então, tipo o PT3, o PT2, né? Urânio alumínio, urânio selênio, urânio estânio, quer dizer. Tá? Essas duas são classes distintas que a gente está tentando entender. E, em geral, os supercondutores de alta temperatura estão nessa classe também, porque são, inclusive, anisotrópicos. Então, o interessante é que o modelo ele funciona bem para um metal que tem densidade de portador constante e que é isotrópico. Aí o modelo parece funcionar.
Ótimo. Obrigado, Carlos.
Eu que agradeço, Diego. Foi um prazer.
Gracias, Diego. Bueno, I would like to make a comment, if Fermi allows me, about the great Simón Bolívar, the general of Venezuela, in his struggle against the Spanish for liberation of the Spanish domination. And we here in Pernambuco, in Brazil, we are very proud because we had a guy from Pernambuco that fights together with Simón Bolívar. They were very good friends. And his name is Abreu Lima. And I was very glad when I was in Colombia to see there was a monument to the general of this libertation fight. And there is our Abreu Lima. And the sad thing for this commemoration for me is that Simón Bolívar, died very, very young. He had only 47 years, and he died from tuberculosis. And this was the last battle he participated, was few days before he died. But Abreu Lima continues to be working, let I say this way, with the other general for the libertation of part of the Latin America from the Spanish domination.
He was very friend of José de San Martín from Argentina.
Yes, also, great people.
Aliás, acho que fue José de San Martín quien colocó a Bolívar nessa rota
luta
libertadora.
Sí.
Não sei que pode falar, Diego, disso aí.
Diego,
Sí,
¿tienes algo a acrescentar?
Sí, no, la verdad que un día especial para América Latina. No sé mucho qué comentar más que decir que es un día especial y que bueno, que le agradezco al profesor que lo haya recordado, ¿no? Es un día importante.
Sí. Also, Diego, I would like to tell you, I will speak in English because I want that Stuart understand.
Okay.
We are all hermanos tomorrow in the battle against France. Let's
Yes.
cheer for Argentina. Okay?
Sí. Oh, gracias.
Okay, we are Latin American people, guys.
Sí, 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 gracias.
Okay, before giving you all the word again, Carlos, I would like to tell the following. This is the last meeting of LAFMAT, Carlos, of this year. Yeah? It's a special day, and that's why you were invited for this special day. Okay?
Unbelievable, my friend. Thank you very much. You
see,
are kind of
There
friend,
is
my
a conspiration from the start for you to come to join us. And we are very glad having you here, and we are very glad in having this network working for more than 1 year. And we will stop for Christmas holidays, except that next Saturday, our meeting will be at 12 hours Brazilian time, and it will be delivered by Santa Claus. Everybody is invited, okay? By Papai Noel. And we will restart by the end of January. I have in mind the date is 28. All this stuff, I guess, yeah, is the last Saturday of January. Okay? And before ending, let me ask first Melvin James James. Tenemos pregunta de lo público peruano.
Gracias, profesor Albino. Saludos, profesor Carlos. No tenemos como tal preguntas, pero sí felicitaciones por su presentación, profesor. Gracias.
Gracias,
Nós que agradecemos.
James. Ximena, por favor.
Buenos días a todos. No, aquí no tenemos por estas redes preguntas del público, solo agradecimientos y felicitaciones por la charla del día de hoy. Muchas gracias.
Gracias, Ximena. Eliana.
Buenos días, profesor Albino, gracias por el espacio como siempre. Profesor Carlos, no, igual muchísimas gracias, no tenemos preguntas.
Bueno, gracias, Eliana. Profesor José Fermi, tenemos preguntas del pueblo venezolano.
No, numa hora dessa, o povo tá na praia. Eu só tenho um comentário aí pelo WhatsApp. Muchas gracias, profesor Carlos, por la conferência. Muito obrigado pela sua palestra.
Eu que agradeço, José. Viu? Um prazer imenso poder dividir com vocês.
Ok.
A gente segue em contato.
Professor Felipe Mondaca, temos pergunta do público de chileno. Felipe? Alô, Felipe? Não escutamos nada. Felipe, open your camera and the microphone, please. We cannot hear you.
Por aquí, por Chile, por aquí en el sur no. Hola, ¿se me escuchan? ¿Se me escuchan?
Gracias, Felipe. Agora.
No hay preguntas.
Gracias. And now I would like to ask Sergio, Professor Sergio Conejero.
No, en esta ocasión no hay pregunta. En esta ocasión.
Ok, gracias. Entonces, Before ending, Carlos, I should mention again that this network is organized by several universities. Universidade Nacional Maior de São Marcos, a Decana das Américas, a Universidade de Barranca, em Peru, Universidade Nacional de Colômbia, com sede em Bogotá, em Barranquilla, e a Universidade do Norte, todas em Colômbia, Universidade de Zulia, em Venezuela, o Sinvestaf e o Centro de Investigação de Materiais Avançados em México, a Universidade Católica do Norte, em Chile, Universidade de San Sebastián, desculpe, sorry, also in Chile, University College London e University of Cambridge em UK. E Universidade Federal Rural do Rio de Janeiro e Universidade Federal de Pernambuco, no Brasil. So, by saying this, I
¿Vino? O yo estoy mal con la transmisión, o o Albino está, se ha congelado.
Acho que ele está congelado.
Ok, bien, entonces mientras se conecta, a todos muchas gracias, ha sido un año muy especial, con muchas palestras. El día de hoy el profesor Carlos dos Santos está cerrando el ciclo de palestras de 2022, y dependiendo del profesor Ángel Bustamante, que es el que paga los Zooms, la suscripción de Zoom, el otro año tendríamos nuevamente las transmisiones del 2023. Entonces, Ángel, por favor, nos confirma durante las siguientes semanas, Ángel Bustamante, si es que continuamos mediante Zoom para el otro año, ¿ya? Se ha abierto muchas colaboraciones. Empezó este proyecto, esta red, a fines del año pasado, 2021, y durante el 2022 ha ido creciendo más y más, y ya tenemos la participación de muchas universidades de Latinoamérica, ¿no? Recientemente se ha integrado a la red el profesor Diego Lamas de la Universidad de San Martín, y quien va a hacer las transmisiones en Argentina, y va también a transmitir las preguntas del público a la red todos los sábados a partir de después de mediados de enero. Bien, Albino, ya volviste, continúa.
Gracias, Luis. Tú estás siempre pronto, hombre. Entonces, acá, bueno, Carlos, ahora es tu momento de decir algumas palavras a mais.
Muito bem, tá bom. Albino, muito obrigado pelo convite. Tá? Gostaria de dizer que foi muito interessante poder fazer essa apresentação. Como viram, não é algo simples de ser feito, porque envolve, no manuscrito, tem centenas de equações. Mas o que eu gostaria de dizer é o seguinte: fico muito contente de ver aí a capacidade de vocês, dessa colaboração internacional, principalmente aqui nas Américas, né? Na América Latina. Queria parabenizar vocês por isso, fiquei muito feliz, o Albino sabe disso, já tive a oportunidade de conversar com ele, viu? Desejo sucesso para vocês em 2023, que vocês tenham muita paz, saúde, e que continuem firme, e no que depender de mim, Albino, eu estarei sempre aqui, meu amigo, viu? Você sabe disso.
Gracias, obrigado.
Obrigado.
Thank you. Okay, now it's time to end this meeting, so I will call the chief. Luis, por favor, Luis. It's your turn.
Bien, muchas gracias a todos, amigos, todos los miembros de la red, que tengan felices fiestas de fin de año, Navidad, Natal y un nuevo próspero año nuevo 2023. Nos estamos viendo luego del mediados de enero. Y otra cosa más, antes de terminar también, darla, si alguien más quiere hacer un comentario, pero antes mencionar que debido a esta, o gracias a esta colaboración, a esta red, también se han formado nuevas alianzas y se están viniendo movilidad entre las universidades. Por ejemplo, la estudiante colombiana de doctorado, Ximena Velázquez, está viajando a la Universidad de Cambridge y al University College of London para trabajar con Stuart Holmes en febrero. Ya tiene su pasaje, su carta de invitación y la visa ha postulado las próximas. También otro estudiante de la Universidad de San Marcos de Perú también está viajando próximamente, mitad del otro año, en mayo, está viajando también a Cambridge para hacer pasantías por medio año. Todo financiado también, gracias a estas redes que estamos creciendo y creciendo cada vez más. Perfecto. ¿Alguien más de ustedes desea hacer algún comentario o alguna precisión? Si no, para terminar la transmisión.
Please,
¿Nadie más?
ask people to open the camera, just to say.
Okay, please, open your camera, everybody. Por favor, abran sus cámaras todos para decir hasta el otro año, hasta el próximo año, ¿ok? Abran sus cámaras todos para despedirnos. Gracias, Carlos Dos Santos.
Feliz año.
Feliz Navidad.
Merry Christmas.
Gracias.
Feliz Natal y buen año nuevo.
Feliz Natal.
Ángel, paga el Zoom, por favor. Paga la suscripción del Zoom, por favor, para el otro año.
Papá Noel va a pagar eso.
Papá Noel. Bueno.
Hasta luego.
Ok, nos vemos ahí. Chao.
Ya. Cortar la transmisión.
Ya.
Cortar la transmisión.
Ahora,
No.